Hello, in this video I'm going to show you the options of the Microsoft Fabric data layer. There are multiple options for storing data in Microsoft Fabric, but which one's the best for you? To try to help you understand the data storage options, I'm going to look at the history and how they developed over time. But first a disclaimer. The history part of this video is largely built on my personal experience and what other people told me. It's never meant to be the perfect history lesson, but to help you better understand the Microsoft Fabric data layer. I'm going to start this video with the same picture I'm going to finish with. This is Microsoft Fabric, and we're going to look at the Microsoft Fabric data layer, which are these components. These are the warehouse, lakehouse, Kusto DB and dataset. If we want to look at it further, we're going to explore three threads over time. The first thread is going to be the business applications and business intelligence development. Then we dive into the internet, and in the last one I'm going to look at the cloud, what that brings to the table. In the end of the video we're putting it all together in Microsoft Fabric. The first thread I want to explore, business applications and the later rise of the business intelligence. 1972, relational database design. In 1972, Edward F. Todd published a paper on a relational database design. He's regarded the inventor of the relational database, something that got very popular over time. Now remember, in 1972, the computers were mostly IBM mainframes, and they were big, chunky and very expensive. And they were also mostly used by large companies and to some extent universities. The main application of these systems was mostly the automation of financial systems like general ledger and payroll. Up till this time, these systems were mostly used index files to store their data, and it was up to developers to make sure that the data was consistent. If there was a software error or something else, then it could lead to inconsistent data. The answer to protect the integrity of the data was to define relationships between the tables and to enforce these relations. In this way, there would be no inconsistency of the data. Example of this would be the sales orders with the customers, like you see in this example on the sheet. The database would guarantee there would always be a customer, so you know who orders it, where to ship to, and who has to pay for it. Remember, we're still in the early 70s, and databases was all about financial programs, and it was not a good thing to lose information in a financial system. Next stop on the timeline is 1983. IBM introduces DB2. Things were moving rather slowly, and it would take 11 years for IBM to release DB2. The main reason it took so long was that IBM was afraid that DB2 would compete with the previous product IMS. IMS is the system they already had and worked with index files. The name DB2, that would raise the question, was there also a DB1? Not really. IBM referred to IMS as their first database system, so any successor would therefore be called DB2. Although DB2 was released, adoption was rather slow. Any existing system based on IMS would be continued to be used for years to come. Shortly after DB2 was released, Oracle and Sybase, at that time still known as Systemware, also released their database systems. In 1988, the International Conference Multi-Rate Data Analysis Consortium was held in Rome, and it was at this conference that the name business intelligence emerged. The value of data was recognized, and business intelligence as a separate specialization has started. In 1988, if you wanted a report, you got something like this. A paper print mostly with alternating white and green lines and something that could be tens of pages long. Accountants and controllers loved these reports, but for management they were rather useless. Most systems in use were individual silos and only had limited options to combine data from other sources. As mentioned, IMS was still in use by most systems, and the only way to access the data was developing special code that would access the data. The options to query the data were very limited at the time. Another thing that most systems could not handle was the workload of heavy reports. The database systems were designed to support applications. They were optimized to populate a screen with only few records at a time, like a screen with customers and information on later sales. If you wanted a report based on an entire table, the system would struggle, and it would interfere with the daily business. So to run a report, it had to be scheduled as a batch process and runs outside of the business hours. And the main reason for all this is that hardware was very expensive and only very limited capacity at that time. What happened a lot is that someone took these paper prints and entered the data in a spreadsheet to create reports for management. This way of working contributed to the popularity of spreadsheets like Lotus 123. To support more ad hoc queries and reports, it was a common practice to make daily copies of separate databases to be used only for reporting and analysis purposes. By the end of the 80s, it was getting more and more practice to copy these exports to a separate database and combine the data of multiple systems. Such a database was called a decision support system, and in this way, it was much easier to create management reports. And this is how business intelligence was born. In 1989, Microsoft released the first version of SQL Server, also called SQL Server. It actually was not a separate program, but Microsoft licensed Sybase, and it did not even own the source code. It was only later, in 1998, 11 years later, SQL Server version 7 was released, and it was the first version independent of Sybase, where Microsoft owned their own code. Our next stop on the timeline is 1993, a year which online analytical processing was introduced. Code released a scientific paper on online analytic processing, also known as OLAP, and this was a new way to design the tables of a database. Until this time, it was common to develop databases on the principles of online transactional programming, also known as OLTP, which was based on designing tables by the rules of normalization. OLTP was focused on protecting the data from inconsistencies and relied heavily on eliminating redundant data. This new database design of OLAP, however, was completely the opposite. In OLAP, you don't care so much about inconsistent or redundant data. The data came from a source system, and this system was able to work with that data. OLAP is focused on aggregating of numerical data. As mentioned, the source systems at this time were mainly financial systems, so it was all about aggregating financial data. The design is based on dividing the data between fact and dimension tables. The data to be aggregated is concentrated together in the so-called fact tables. On the other hand, the data that should be aggregated by, like products, departments or time, are concentrated in other tables, the so-called dimensions. This creates a database that's very good in aggregating and filtering large volumes of data. This results in a star schema that looks like this. Here you can see the sales data in the middle. This is the fact table to be aggregated, and the time, products and geography on the outside as dimensions. Officially it was called multi-dimensional views and made slicing and dicing easy. Often the design is portrayed as cubes, where you can filter or aggregate slices of data. It works the same as a pivot table. It's worth noting that the paper of code was retracted in the end. As it turns out, he was paid by a company to promote this technology. He should have disclosed this information in the paper, but he did not. Secondly, the idea was not quite new, as there was already a product available based on this technology. However, the idea of OLAP was quickly picked up by mainstream manufacturers, and in 1998, Microsoft released OLAP Server named Analysis Services, later known as SSAS. In 1996, an important book is published on how to set up a data warehouse. The Data Warehouse Toolkit from Ralph Imbal. This book turns out to be the standard for the data warehouse until today. In this book, Ralph Kimball takes the online analytical processing design to the next level and describes an architecture to a full-scale solution to create a single data warehouse that combines the data from multiple source systems. He called this the single version of the truth. The way he achieves this is by creating multiple steps to combine the data from the source systems into a single data warehouse. The data is first copied from the source system to a staging area, and from the staging area the data is integrated into a data warehouse. This data warehouse is designed as an OLAP system with fact and dimension tables. Next, for different projects and data consumers, a subset of the data warehouse is copied into multiple data marts. A data mart only consists of the data needed for the specific project or reporting solution. The main reason to create a data mart is that the system that hosts a data warehouse is often not powerful enough to handle all the load from the reports that are built on top of this data warehouse. We are still in the 1990s, and the performance and the compute of storage was still limited, and also very expensive, especially compared to today. On top of the data mart, the reports and analytical solutions were created. Now I jump from 1996 to 2012. And your question will be, has nothing happened in between? Actually, a lot had happened, but not when it comes to new technology. The tools got more mature, systems got better, faster and cheaper. As the cost of automation were reducing, more and more processes got automated. As a result, more data for the data warehouse was collected. Especially web applications have the tendency of generating vast amounts of data. As I mentioned, hardware was getting more powerful and was able to keep up with the increasing volume of data. I remember visiting a data center of a client at that time, just to find out that the floor space was only half used. It was practically half empty. The architect who built the data center explained to me that the data center was built for growth. And yes, the amount of data and compute was growing, but at the same time the hardware got more powerful, more compact. As a result, the occupied floor space of this data center was kept as the same over time. The compute was getting faster and faster, but what did not get faster was the storage itself. In this graph you can see that between 2000 and 2020 the storage increased about 12 times in speed. At the same time, network speed gained from 100 megabytes to 10 gigabytes, which is an increase of 100 times. The speed of the storage was not keeping up with the growing amount of data, and as a result systems kept waiting for the data to arrive. SSD was available in 2012, but it was still very expensive and not a real option for storing large volumes of data. When we go back and have a look at the architect of Kimball, the steps between the different stages are taking up more and more time. Most of the time the systems are waiting just to get the data from storage or to be written to storage. A common refresh rate of a data warehouse is a daily refresh, where the refresh happens outside of business hours during the night. It was happening more and more that a daily refresh was not ready by the start of business day. Let me explain more in detail how that works on a database system. A traditional database, the query was processed by a CPU and it gets the data from disk. One server had multiple CPUs, and by using multi-threading, processing the query can be done in parallel over multiple CPUs to speed up complex queries. That worked well for OLTP, transactional processing, that only required a few records at a time, but for queries that process large volumes of data, the CPU was mostly waiting for data to arrive from disk. Hardware vendors came up with a solution called Massive Parallel Processing, or MPP. Basically, CPU was given its own storage, and the data was partitioned over the different compute nodes. A central host node is used to coordinate all the compute nodes. MPP gave a boost in performance, not rivaled by any traditional system at that time. Actually, MPP was nothing new, as some mainframe systems, like the Tandem, already used this method of partitioning, but it was perfected for data warehousing workloads. MPP worked best on databases designed as OLAP, with fact and dimension tables. Two systems that came on the market in 2012 are the Microsoft Parallel Data Warehouse, or PDW, and the IBM NetTeaser. The Microsoft PDW is a big system. The picture on the left shows one node, and it has a style of American-style refrigerator. For a working system, multiple nodes are needed. The picture on the right shows a configuration of 5 nodes. Although the PDW had a very good performance, it never really got popular. And there are two main reasons for that. First, as it uses partitioning table over multiple nodes, that complicates updating and inserting data, as it requires additional overhead to coordinate between the partitions. This results in a somewhat limited set of SQL statements. Secondly, the system is fast, but it came with a very big price tag. 1 year later, in 2013, the concept of data virtualization emerged. Same problem with slow storage, but a different solution. As we have a look at the architecture of Kimball, it requires a lot of copying data. With data virtualization, the data is actually not copied, but left at your original location, and subsequent systems would only reference the location. A bit like creating views on an underlying database. The data virtualization layer is created to connect the reporting and other data consumers to the data sources. In its most basic form, the data would be taken directly from the source systems, but as we've seen earlier, these source systems were not capable of handling that workload. However, with data virtualization, the number of copies is significantly reduced. Data virtualization was received with a lot of enthusiasm, but in reality it was difficult to set up, as connecting systems from different vendors proved harder than hoped for. So far on the first thread about business applications and business intelligence. This thread was all about the more formal business applications and BI solutions provided by centralized IT teams. The next thread we're going to look at is what the Internet brought to the Microsoft Fabric data layer. In 1993, in the Netherlands, that's where I'm from, the Internet was introduced to the public by Access for All. So far, the internet was the domain of universities, students, researchers and early adapters. The University of Twente was one of the frontrunners in this. It was not until the year 2000 that the internet got broader appeal by the public, and something like surfing the digital highway has started. And with the new kind of audience came a new kind of website. So far, most websites had static content that only changed when the website changed. But now we see websites with dynamic content, like user forums, where people can enter posts and they can give reactions to these posts. And with the new website came a new generation of developers. These developers were mostly students, still at school or just graduated, and had no background in developing business applications. They had a couple of things in common, and first and most important was that they had only limited funding for these projects. The tools from the previous tranche were developed for business applications and not for web applications. So the existing database systems were all about financial data and numbers and not storing text from user input. Besides, these tools were targeted to enterprises with a healthy budget. The new developers started to make their own tools, and they did that together in open source projects. In this time, over 200 different database systems have been developed. These databases are called NoSQL databases and had a completely different approach than the relational databases used for the business applications. The goal was to easily store and retrieve information, in most cases text input or even complete documents. In contrast to the existing relational database systems, who were all about protecting data against inconsistency and data loss, this protecting created overhead and restrictions on what you could do and had quite a learning curve. And all the new generation of developers wanted was an easy way to store data. These new database systems can be divided into a couple of categories. The most important are Key Vault Store like Redis, Document Store like Elasticsearch and MongoDB, and multi-model. They can behave like multiple categories. Example of this is Cosmos DB. Did any of these new databases make it into Microsoft Fabric? Actually, no, but it paved the way for something else. In the wake of the open source NoSQL projects, in 2003, Google started a project called Hadoop. The reason they started this project is they were looking for a better and a cheaper way to store the data collected by the search engine, so they could analyze it later. In that sense, Hadoop is not a real database, but more a file storage platform. Hadoop was originally designed for computer clusters built from commodity hardware like regular PCs. The project started as Hadoop file system and additional tools were added later as a collection of open source projects. The most important of these additions is MapReduce. Hadoop file system is made up of a central node that manages multiple data nodes. There can be up to 500 data nodes in a single cluster. The data nodes store the files. To have a more resilient system and avoid data loss, the files are stored over multiple nodes. This looks a lot like the MPP, the massive parallel processing we saw in the data warehouse appliance earlier, but there's one big difference. Hadoop spreads the files randomly over the nodes, and Hadoop has no idea where the data is. The parallel data warehouse, however, uses a partition key, and it knows which records are stored in which partition. To query the data, MapReduce is used. MapReduce does it in two steps. First, it executes the map phase, where all the needed file chunks are located on the data nodes and the data is extracted from the files. In the second phase, the retrieved data is aggregated and processed by the reduce phase. And finally, the result is returned. This, however, is a batch operation and it can take some time to deliver the results. This is in contrast to a real database system, where you can expect results pretty immediately. The Hadoop project continued to improve over the next years. In 2006, there was the first release of Hadoop, and Twitter, Facebook and LinkedIn started to use it. In 2008, Hadoop was part of the Apache program, and Cloudera was the first commercial release. Although Hadoop is an open source platform, having a commercial release meant there was official support for companies now. And having an official support for Hadoop makes it more attractive for projects that have to focus on productivity and system uptime. We fast forward to 2011 and we found ourselves in the middle of the big data hype. Hadoop has evolved in a more mature and enterprise-ready analytics system and is gaining a lot of more traction by now. Artificial intelligence and machine learning has been a domain of scientific research for mathematics, medicine and astronomy so far, but it now makes its way into the business intelligence. And this is all made possible by Hadoop because it can analyze and collect a lot of data in a short time, or analyze it later with languages like Python or R. It's clear that AI now has made its way into business intelligence, and these new possibilities come with a big hype. Did this hype deliver on its promise? To some extent. As with all hypes, the gain was not as big as expected or promised, but AI and machine learning are here to stay within business intelligence. And I think the biggest achievement of the big data hype that it did not get unnoticed by the BI people from the upper trend line. It's not a coincidence that about the same time, the data warehouse appliance and the data visualization popped up. The vendors of the basic BI tools had to do something in reaction to the big data hype. It's only now they start looking at options to handle large data loads and incorporate AI possibilities in their tools. Meanwhile, the development on Hadoop continued, and 1 year later, in 2012, Apache Spark was released. Apache Spark is actually an improved version of Hadoop. Where Hadoop is mainly batch-oriented, Spark is an interactive-oriented tool. One of the principles of Hadoop is to use cheap hardware. The workload is batch-oriented and makes best use of the available hardware. In Spark, this principle of using cheap hardware is abandoned. I do remember working with the data science at that time, and it was quite common for them to start a batch process in the morning and not expecting any results until after lunch. For companies, time's money, and they would prefer a system with higher productivity and faster results. Spark is a memory-based technology that can deliver these results much faster. The drawback, however, is that Spark needs a lot of memory, and it means the use of expensive hardware. For projects that prefer productivity, Spark is a better option, but projects with limited funding are better off with Hadoop. Tools like Databricks, Azure Data Factory, and serverless pools of Synapse are built on top of Spark. As we've seen multiple times in this video, a new technology gives new possibilities. With Spark being interactive and in-memory technology, it makes near real-time analytics possible without additional and specialized tooling. So far, all the technology discussed in this video is batch-oriented, like the traditional data warehouse with the Kimball-style architecture and Hadoop. The introduction of Spark makes it possible to analyze data as it comes in. And again, streaming analytics, just as data science by itself, is not new and existed for a while, but the availability of new technology makes it possible for BI to pick up on this. For streaming analytics to work best, only minimal transformations and cleansing is done on the data as it comes in. That works great on smaller data sets, but when the data set gets larger over time, it will complicate and slow down retrieving the data. Working with streaming data only works well when only working with the most recent data and you don't keep too much of history. A way to preserve history while having the most recent data is to use the Lambda architecture. This architecture is a combination of real-time processing for the most recent data and batch processing for the history. Every hour or day, or depending on the project, a collected data is processed into a single database. Any history is then removed from the real-time layer. A serving layer combines both data sources into a single data source. A variation on the Lambda architecture is the Kappa architecture. This one has a different way of synchronization between the real-time processing and the batch processing. And with that, I'm at the third and the last thread of this history timeline, the cloud. As the use of the internet keeps growing, so does the infrastructure that supports the internet. The most important part of the internet are the communication cables, and quite a lot of these cables run on the bottom of the ocean. This map shows the locations of the communication cables on the ocean floor, and it's clearly visible that a lot of these cables run between North America and Asia, and between North America and Europe. So what's called the cloud, at least for some part, is on the bottom of the ocean. Having this large and reliable data network does not make it necessary anymore to have servers and storage physically near to you. They can even be on another continent and still have reasonable performance. At first, vendors offer space in one of their data centers where you could have your own server or you could use one of their servers. But over time, they shifted to offer services instead of servers. The advantage was that you did not have to worry about the infrastructure itself, just use the service. The first services offered were platforms for storage and web apps. The cloud itself did not fall from the sky, and up till now its main use was mostly websites and web applications. It was around 2006 it was also interesting to host business applications in this way. In 2006, Amazon started their Amazon S3 storage and Amazon Elastic Compute Cloud. In 2008, Google started Google Cloud Computing. And in 2010, Microsoft launched their own cloud service, Azure. Azure started small with only a few options. The first generation of Azure offered already a version of SQL Server called SQL Azure. Over time, more services got added. For Microsoft, offering these cloud services is a very interesting concept. Not only provide they the software, but also the hardware. For on-premise software, Microsoft must test this software on at least dozens of different combinations of hardware that is used with customers all over the world. For cloud services, however, they only have to test the hardware for their own data centers. That means quite a reduce of cost for testing. Furthermore, updates, new features and releases can be deployed at any time for cloud services, where on-premise software has a release cycle, and it can happen that new functionality must wait for 2 years to be available for customers. At this moment, Azure is the largest source of revenue for Microsoft. Since the introduction of Azure, Microsoft spent a lot of effort in adopting on-premise software and make it available in Azure. A very successful formula is combining existing functionality into something new, where the combination creates interesting possibilities. And one of these possibilities is introduced in 2015 as Power BI. Power BI was created as a combination of an Excel plugin and Power Pivot. And Power Pivot on its turn is based on the OLAP cubes. In the same year, another interesting Azure service was released. Remember that data warehouse appliance that Microsoft introduced in 2012, where you had to buy this very big appliance? That was made available in Azure with the name Azure SQL Data Warehouse, also referred to as Azure DW. Now you only had to create a resource in Azure and you didn't have to buy that big box. And suddenly, it was a very interesting service, and it did really get big up momentum this time. In 2019, Microsoft took it up one notch, and they introduced Microsoft Synapse. Azure SQL Data was combined with Apache Spark, an option to virtualize data, and was renamed to Azure Synapse. For the first time, traditional business intelligence is combined with data science in one product, and this created again new possibilities for BI projects. And it didn't stop there. In 2023, Microsoft introduced Microsoft Fabric as an all-in-one analytics solution for enterprises. And Microsoft Fabric on its turn is a combination of Power BI, Synapse and Azure Data Factory. And this brings me to the last part of this video. So far I talked about the IT components that make up the business intelligence landscape. Now it's time to look at how it's all brought together into Microsoft Fabric as one unified platform. This is the picture again from the start of the video, but now with the timeline I previously talked about. On the bottom there are 4 data storage options, as we have the warehouse, lakehouse, Kusto DB and the dataset. The dataset is derived from the online analytical processing and more specific the table engine for analysis services. The dataset is very good in compressing data and optimizing it for querying with DAX. The data warehouse is built from the technology that started out as a data warehouse appliance and was further developed into Synapse. The data warehouse is optimized for fast retrieving of structured data, especially if that data is structured in fact and dimension tables. Data virtualization is a technology that's incorporated in the Fabric as general. All data options have the possibility to link to other data sources. The lakehouse is built on top of a Spark cluster. By using Spark, the lakehouse can handle structured data that's stored in tables, semi-structured data like CSV, JSON or Excel files, and unstructured data like plain text files. Kusto DB is the option for real-time processing of data. If you worked with log analytics before, the Kusto DB should be very familiar, as it is the same technology. Kusto DB is very good at handling application and sensor logs. It's for handling data that does not change anymore after it's been added to the database. And finally, Power BI is still available as one of the many options to explore and present the data from Microsoft Fabric. I would like to finalize this video with the strengths and weaknesses of the different data storage options. The warehouse is best used for more formal reporting and makes a good choice for large and very large databases. The warehouse restricts you to more formalized data structures, but at the advantage of very fast delivering of data, as it uses the massive parallel processing engine. In contrast to the warehouse, that only can handle structured data, the lakehouse can handle structured, semi and unstructured data. This makes it less restrictive and gives more opportunities to explore the data in the way you want it. Keep in mind that using semi-structured data and unstructured data gives great flexibility. It comes at a performance cost, as every time you query the data it needs to be parsed and transformed. When you want to work with machine learning models, a lakehouse is also needed. If you start a project and you're not sure to use a lakehouse or a warehouse, often it's best to start with a lakehouse because of flexibility. It is not possible to change a lakehouse into a warehouse and vice versa afterwards, but you can create both options in the same workspace and work with them side by side and use the data from the other storage option. If later turns out the warehouse would be a better option, you can always copy the data over and work from there on. The Kusto DB is a purpose-built database, especially for streaming data. If the data from the Kusto DB is to be combined and enriched with other data, it might be a better option to copy the data over to a lakehouse or warehouse with a more formal structure. And the last data storage option is a dataset, meanwhile also renamed to semantic model. When creating a warehouse or lakehouse, it comes with its own semantic model, so it's not always needed to create a separate dataset for Power BI reports if it's built on top of a data from a lakehouse or warehouse. However, the dataset is still needed if you need to pull in additional data outside of Fabric, or if you need some additional transformations in Power Query on top of the available data. It is noted that the dataset itself is actually not a real data storage option, but more like a caching mechanism. Every time a dataset is refreshed, new data is pulled in again from the data source, and the old data is deleted. You still need to store the data itself in the original data sources. And this concludes the video on the history of Microsoft Fabric data storage. I hope you liked the video, and thanks for watching.